who's going to talk about water waves. So this is Malte, and that's my pleasure.
Oh, thank you very much. Thank you very much to the organizers for inviting me to give a talk here today. When Gennady asked me, he said I should try to bring in a few applications as well, and sort of different applications. And so I decided on this topic, and I'll talk a bit about water waves as well, just so you sort of get an impression for those who are not too familiar with it. And then I'll be talking about submerged plates, and I'll focus on one particular type of plate, and then sort of talk about extensions and sort of show where why is this important for, or why is this interesting to be solved by the Wiener-Hopf technique, and where do the difficulties come in, and what changes if you use different plates. And while sort of as a little disclaimer, in the end I won't be talking about matrix problems. I will sort of hint to matrix problems, and you will easily see where they come in at the end of the talk. So before I start, I thought this is the talk, the first talk after the dinner, and so I should try to start with something nice to look at. And let me see whether I can do this. And this is this. So what do you see here? Maybe I should stop this. So this is, what do you see here? So this is a wave flume, water wave flume. You see here cylinders which are sort of stuck to the bottom of it. There's a sort of a glass window here so that you can look into it from the side, and there's a wave maker here at the back. And so basically the idea here is you produce waves here through a wave maker. Waves travel down the flume. You see sort of half of it, so it sort of looks like precisely like that on the other side. And you're interested what goes on here in the middle, and then sort of the flume has a major deficiency, as all those flumes have, and that is it's of finite length. And this is really annoying, because if you run experiments, eventually the waves will hit the back and they'll be reflected, and by the time they reach whatever you want to look at and investigate here, it sort of completely muddles up your experiment. So there's three reasons for showing this video. One is sort of a little acting as a, well, first one I mentioned, to show something nice after the dinner. Second one is it's supposed to be a bit of a teaser. This video was taken at the beginning of the year at the University of Perth, or the University of Western Australia in Perth, I should say correctly. And what we're interested in here is water wave scattering by bottom-mounted cylinders, which basically were in this wave flume. They sort of mimic an infinite array. The windows here, or the sides of the flume, acting as mirrors. And what is interesting about the setup here, I won't be talking about it today, as I said, this is a bit of a teaser, is these cylinders are arranged in a certain way that you get very high responses in between certain cylinders, depending on the frequency of the incident wave. I'll just let this run. So this was a wave packet experiment. You can see Hugh Vogelmott walking into the movie. So the wave has passed, and so basically what you maybe stop a little later, and so what you can't see too well in this movie, but as I said, talk's not about this, so I won't be going on about that, is that between these cylinders here is you basically excited a mode which will persist for quite a while. And depending on the frequency of that incident wave, the mode will persist in between different cylinders. That's sort of the setup. And what is interesting about this is this effect known as rainbow trapping is reasonably well known in optics. But what is nice about these experiments, at least to my knowledge, is the first time that it was observed for water waves, and it has we have some ideas on how to use it possibly, or similar effects, for focusing of wave energy for power takeoff devices in the ocean. Anyway, so this is not really related to the talk. The relation to the talk is, as I said, the very end of the flume. You need to damp the waves, And how that is usually done, you don't see that in this video, I have a sketch here. How this is usually done is in the following way. So this is the flume from the side, so now my object here is floating, but it doesn't really make a big difference. So on the one end I have a wave maker, and so one option of doing this, there's different ways, is to install a porous plate here. So either one or a few, you can have them sloping to look a bit more like a beach. But that's sort of the idea. So maybe I should draw a sketch here, because we'll see that. Where is my... Ah, here it is. Because we'll see that rather often during the talk. So basically, what we're interested in. So we have a bottom. Then we have our waves, and so I'll be talking about this finite size problem later on, in particular with the finite length porous plate. For now, let's just assume there is a. Well, I probably shouldn't draw it right in the middle. We have a plate like this, and so to introduce coordinates as well for later use. So here, this is the x-axis. There's 0 here, and I have z-axis here, and the still water surface is at 0, and then to get this right, I have minus h here and minus d. Does that? Maybe I should write a bit larger letters. Right, and so these. So this is the problem I'm wanting to talk about today. Is how can we solve the problem, particularly for porous plates. Later on, I'll also talk about rigid plates. They're often used as breakwaters near coastlines, and the interesting thing there really is if it's also elastic. So if an elastic submerged plate, yeah, we'll talk about that towards the end of the talk. We'll see how it pans out with the time. So for now, we'll just look at one submerged horizontal plate. Okay, so this problem, it's a 2D problem. It doesn't look that difficult to start out with. And usually what people do, and this has been done in the past, they use what is called eigenfunction matching. If you're familiar with the technique, that's good. If not, it's what you basically do. You split your domain in half. You expand the problem in eigenfunctions on this side, you expand it on that side, and then basically you use continuity conditions along the artificial boundary that you introduced, and get an infinite system of equations for the unknown coefficients in the eigenfunctions and expansions, and you truncate and solve numerically. And that works reasonably well. Problem is there's a few problems. One problem is that they're typically eigenvalue problems that you have to solve. We'll meet them during the talk as well, and they may not be self-adjoint. And also what happens is, well, in the end you'll always encounter dispersion relations. I'll get into that as well during the talk, and they may be quite nasty. And the other thing is that the eigenfunction matching method is typically quite slowly convergent. If you're not too interested in high accuracy, that's sort of for practical, more like engineering type purposes, that's usually not a big problem. But if you sort of look at it more closely, you realize that it is rather slowly convergent. So what I want to do is take a different approach and, well, obviously use the Wiener-Hopf technique. And I want to do that to solve the problem for the semi-infinite plate. Which is why I've drawn my sketch like this over here. And I also want to talk about the Cauchy Integral Method, which I think is not as well known in this context, because what is nice about that is that it does not require knowledge of the roots. So I think it is reasonably well known to you, I think, but generally I always see that it's not as well known. What is also not as well known, this might actually possibly be true for some of you, is the residue calculus technique, which is rather nice because because it's closely related to the Wiener-Hopf technique, but it can also be applied to derive a rapidly convergent solution for the finite plate problem. Okay, so yeah, what is sort of a note on the side is that the one reason for eigenfunction matching being rather slow to converge is that it doesn't build in the square root singularity in the velocity of the edge near the edge of the plate, and these more analytical methods, they do that, which is why if you actually want to use them for computations in the end, they work really well. I mean, you can argue why is the square root singularity in the velocity important, since it's not really physical to have infinitely fast fluid at the edge, but that's in linear water waves, and I mean, for a lot of problems we saw during the conference, that is just due to the model, and that's the equations we have to solve. Right, so I'll focus for most of the talk on the porous plate, but I'll talk about these other results hopefully towards the end, seeing how time goes. Okay, so I should talk a bit about water waves, just for those who are not too familiar with it. So I look at linear water wave theory. So fluid is inviscid, it's incompressible, and I look at irrotational flow. And then typically what people do is they, instead of looking at the velocity potential for potential flow, the gradient of which is the velocity. First thing to do is, well, maybe I should probably write that. So I've got my x, y, z, and t, and what I do is I reduce that to real part of phi, which just depends on x and z. That's the thing here. And then I look at obliquely incident waves. So I factor out an I beta y. That's my y dependence. And the time dependence goes with minus I omega t. Okay, and then my unknown is my complex potential, right? So how does that relate? So how do I get the equations for water waves? Well, I have incompressible flow, so divergence of the velocity should be 0. So if I stick that, if I stick in the relation between the velocity and the potential, I have to solve Laplace's equation.
What is y?
Oh, sorry, y is the coordinate into the board. Yeah, good question. Sorry about that. You're right. So I have that, and I call my water domain omega. So this is in omega. Okay, so then at the bottom here, the typical bed condition is to say that the velocity in normal direction has to be 0. So that's quite simple. I have that dz phi is equal to 0 and z equal minus h. Okay, so what happens at the free surface? So this is basically where the water waves come in, and maybe I should sort of do that as a side calculation here. So I have two conditions. One thing is I have to conserve momentum, and that is in potential flow. It's done by Bernoulli's equation, and for the time-dependent potential I wrote it with a capital phi, so I should stick to that. And then I have P divided by rho plus Gz is equal to a constant, right? That's Bernoulli's equation. And so that's conservation of momentum at the free surface. And the other thing I have to, so now sort of I introduce an auxiliary variable, which is the surface displacement, call that eta. If I do that, then I have a sort of a compatibility condition, or kinematic boundary condition as it's called. The velocity of a fluid particle at the free surface has to equal the velocity of the free surface. And so dz phi, and I switch to the time. Oh, maybe I should, for consistency, do it like this for now. It doesn't really make a difference. Right, so these are my two boundary conditions, and I can now, my auxiliary variable, the free surface displacement, I can now eliminate again by realizing that this has to hold at the free surface. So this is actually eta, at the free surface. And so I stick that in, I take the derivative, and so what I get is I get minus 1 over g dtt phi. Right, and now if I switch to my time independent problem, my time harmonic waves, the tt becomes in minus I omega squared, and the condition I collect, and I'll write that here straight away, is I get dz phi is equal to omega squared over g phi, and that's on z equals 0. Okay, so that's that. So what else have I got? Now I've got the plate. So I said I want to look at a porous plate. And how does it work? What's the condition for the porous plate? Well, a typical thing for porous structures is to look at Darcy's law, right? And we can very nicely do this here as well. What does Darcy's law say? Darcy's law says that the velocity is proportional to the jump in pressure. So maybe call this minus d minus plus minus the pressure minus d minus. Right, so it's the pressure above the plate.
Sorry,
yes.
Just one little question, maybe a bit silly, but didn't you just say that z is equal to eta and not 0 for that previous condition?
Yeah, that's a very good question. I glossed over that, and sort of to see whether anybody feels a bit awkward about that or not. So what you have to, there's actually quite a bit behind this. If you start out with a general setting, you're not sort of 0 is the free water surface, right? So your actual surface is eta. So what you have to do is you have to apply Bernoulli's condition at eta, and you do that in here. And actually, what I also glossed over here is that what you actually have to do here, if you do this properly as well in the fully nonlinear context, you have to apply this at eta as well, and what you actually have here is you have to apply the velocity at the free surface. So you actually have a material derivative to take here, actually here. But if you do a perturbation analysis, you see that in the linear setting, everything is applied at z equals 0. But it's actually quite a tedious calculation. There's sort of quite a few things I glossed over. It's a very good question. Thank you. Right. Okay. So this is just applying Darcy's law. This is the permeability. And you have the jump in pressure. And now I can go back to Bernoulli's equation and work out what is the velocity I can write in terms of the velocity potential, and the pressure I can also work out in terms of the velocity potential by the Bernoulli equation now applied at the plate. And basically what I see, so I get rid of gravity here. So this is, of course, an approximation, but the plate. So I'll just look at a very thin plate, and so it's basically dt phi is equal to p up to a constant rho, the density. So again, dt phi is just I bring down the I omega, and I stick that in here, and what I collect is that the so what do I get? I get dz phi, that's the velocity in through the plate, and that's equal to the jump in pressure. And the jump in pressure, I just said, is something like I rho k times the jump in potential. So, and I abbreviate that by I mu, and then write this as the jump. So this is on the plate. I should probably, yeah, I should say that. So this is gamma p, my plate, and there I have to apply this condition. Okay, so then we've already talked about the square root singularity. So I just write that down here. So this goes as minus 1/2 as the radius, which measured from the tip reads like this, right? So squared, a half. This is always the German one. So a half goes to 0. Right, so these are basically the equations that I need to solve for the porous plate here. Now what I haven't talked about yet, and I'll do that in a second, are my radiation conditions. But just so what do I have on the plate? So I have the porous plate, I have the water domain, and the porous properties are now in this sigma. Did I call that sigma here? Let me just double check. Okay, yeah. So that's what I call this is what is k rho. Okay, we'll have the mu on the next slide. So this is for the I here in front. This is typically a purely imaginary number related to the friction, to the permeability. But you can also introduce an imaginary part, which is then related to the inertia of the plate, if you want to do that. And then in the end, so this is, I think, the form I wrote on here. Yeah. So where is it? Here it is. Yes. So the sigma omega, the sigma is the what I had here is the permeability, I think, over density, right? Should be over density. Oh no, times density. Okay. Okay. So I hope this sort of matches what I wrote on the board. Yeah. So this thing I will call alpha from now on. That's my omega squared over g here. Then the constant in front of the jump is mu. That also matches the board. That's great. And what I didn't say, maybe I should say that on the board as well, is that this is of course taken from the way I wrote it here. What did I write? I wrote something like, d plus. So this is phi minus d plus, and this has to equal phi minus d minus. So I have continuity in velocity, but I have a jump in pressure. Right. Okay. So what about the radiation conditions? So radiation conditions, and I'll sort of be brief about these now. So what I do is I look at what do the waves look like on the left-hand side, when there's no plate. And this is actually quite simple. You can, by a separation ansatz, you quickly find out that they look like cosines, and there's two different types of waves. There's a propagating wave that corresponds to this imaginary root of the compatibility condition, if you like, what turns out to be the dispersion relation, and you also get real roots here, and they correspond to evanescent waves. Right. So where is right. So the important thing to realize is the dispersion relation here, and I'll write it down over here because we'll meet this quite often during the talk, and it's actually one of the points I want to make. And I'll write it in a slightly different form. In this form, this is what people who in the water waves business will recognize in this way. We'll see it written like this: cos kh plus chi k sine kh is equal to 0. Okay, so and what does it do? Well, alpha is our frequency parameter, right? Alpha was omega squared over g. K is the wave number, and so this relates frequency and wave number. So it's a dispersion relation. And the only thing that's maybe slightly confusing at first, but is that I have this correction beta here, which comes exactly from the fact that I have obliquely incident wave, right? This comes in from here. So for simplicity, if you don't want to sort of worry about that, you can always take beta equal to 0, which is just head-on incidence. Right, so if I do that, then I satisfy my equations. I satisfy the Laplace's equation, I satisfy the bottom condition, and I satisfy the free surface condition. So if I'm now interested, so what is the correct radiation condition? Well, if I want to, if I look at a wave of unit potential amplitude, it looks like that. And so what do I want if I go to minus infinity? I want the wave to look like the incident wave plus something reflected, so something traveling the other way. So my radiation condition is phi looks like e to the I kappa x plus what will be the reflection coefficient r infinity e to the minus I kappa x. Then my depth dependence is this psi naught, the traveling wave, the vertical component of it as x to minus infinity. And for the plate region, the plate dissipates energy, right? There's the I here. And so I'll squeeze that under here. Well, maybe not. So that we don't need that. Or maybe I should. So this goes to 0 as x to plus infinity. Right, so this is the system I have to solve. So now we know what we want to do. And so how do we do that? So we want to use the Wiener-Hopf technique. And the trick, of course, is we've seen this many times. Now I think we're coming to territory which is very familiar. So we split this thing up into phi 1, phi 2, above and below the plate. And we have our propagating incident wave, which we take out. So the phi 1 and phi 2 are the scattered waves above and below the line z equal minus d. Okay, and then we do what we've seen a lot of times during this conference. We take half-range Fourier transforms.
May I ask a question?
Yes.
Why the potential tends to 0 at plus infinity? Why do you have no any outgoing waves?
Because of this condition here, if I have my mu here, wave energy is dissipated.
So you have some imaginary part.
The I makes the imaginary part. Yeah, it comes from this condition here. The U, sorry, the pressure. The pressure gets an imaginary part here from the dt.
Because complex wave.
Because it's a complex, and you get and the porosity induces energy dissipation. So because if you've in the semi-infinite regime, you've got a semi-infinite plate, so all the waves are damped eventually traveling down the plate.
That means that you have uniqueness in your problem.
Yes. Yeah. Right. So. Yep. Right, so I take half-range Fourier transforms exactly as I think I can go a bit faster on this here now, also with the adding a small imaginary part to basically open up a strip in the end. You're all very well familiar with that. I'm not going to go through all the algebra, but reasonably quickly you find that basically what you have, what the system of equations turns into this thing here, where you have the what we typically refer to as the kernel function, the k, I have it down here, and then really the unknowns are this d plus, which is the jump on the positive side in the potential, and the q minus, which is the jump in velocity on the negative side. And what is important to note here is that the k of s, and we'll see this popping up over and over again now, the numerator is precisely the dispersion relation. I hope I got that right. So I've switched to Cauchy and shine here for the imaginary parts. But that's just the difference between propagating and evanescent waves, right? So that's that, and that's where the sign difference comes from as well. I should have done that properly. That was so we should switch to the propagating wave. So we have Cauchy here, and this gets a minus, and now it should probably look like that. Is that right? I hope so. here. So gamma is the k, is the shifted k. Yeah, that looks good. Right, that was just the imaginary root was the propagating wave, and then all the real roots were the evanescent waves, which is why I have to change it like this. And what do we see here in the denominator? We see well, it turns out we see the dispersion relation for this region here, including the porous plate. And what is interesting to note there as well is what we see here is we see basically the condition, what happens underneath the plate for a rigid plate, no porosity. What we see here in the multiplicative factor is precisely the dispersion relation for waves traveling above a rigid plate. Right? This is precisely the thing up here, just for not water depth H, but water depth D, so the shallower region above the plate. And then we have this thing here where the I mu comes in, which includes the porosity. So basically we see a whole bunch of dispersion relations here. We see the dispersion relation on the left-hand side. We see the dispersion relation on the right-hand side, which is really made up of something to do with the rigid plate when the mu is equal 0, right? This is for the region below, this is for the region above, and then we have this correction factor here, which includes the porosity. Right, and we'll see that popping up over and over again. So what do we have to do? Well, again, I can go over this rather quickly. I think we have to factor the k in the form where we have something non-zero and regular in the upper half plane and something non-zero and regular in the lower half plane. Okay, so if we can do that, and I'll get to that in a second, we rearrange things in the standard way, and we get something that is regular in the upper half plane. We get something that is regular in the lower half plane on the right-hand side, and then by the usual arguments. You look at the behavior to infinity, it all goes to 0, so a very simple case. So both sides have to be 0, and off you go. Right, I think I have, yeah. So we can then solve for phi 1 and phi 2, and I can now invert the Fourier transform. And I've only done this here to pick out the reflection coefficient, which is precisely the contribution that comes from the simple pole at s equal kappa, the traveling wave to the left, so I get this expression here. And so I have to evaluate the kappa, the k plus and the k minus in kappa and minus kappa respectively. Okay, so that's I think this is very well familiar. So how do I split the k? Well, I can either use an infinite product decomposition. That's actually reasonably straightforward for this problem. It's slightly tedious with the for the denominator because of the porous plate dispersion relation. But basically, what I have to do is I have to be able to factorize the dispersion relation, and this is what we'll always see, and this is very typical for these problems. Problem is, though, as I've pointed out quite at the start of the talk, is that those roots can be quite annoying to find. So I want to proceed in a different way, which, well, as I said, I think for this community is also quite well known. And the trick is to use the Cauchy Integral Method. So basically, we split off this part here, and the numerator. And that splits very easily, and then I look at the remainder, what I call f, and here actually you have to work a little bit. So then I look at this part here. So this is the kd, was the part containing the dispersion relation of the porous plate, and then I have this thing. And what I do is I want to use Cauchy, right? And I think I can go over this reasonably quickly again. So I make use of this formula, being able to identify the parts that are regular in the upper and lower half planes, and then if I do that, I arrive at this formula. So the R infinity, my reflection coefficient, is this thing here, where this I, the Cauchy integral, comes in here, and then I have these additional terms, which are all very simple to calculate. You can see that here, and then I have my chi, which ensures convergence of the whole thing. So, and the I probably was a little bit too quick here. The I, this integral is very easy to calculate numerically because the integrand is regular at t equal 1. So it's not as nasty as it looks at first. So it's actually very, very quick and easy. So I can do that, and here's the answer. The great thing is I don't need any knowledge of the roots of the dispersion relation for the porous plate part. Right. So what I can also do, if I then say, well, I do want to look at the roots, I can actually recover the infinite product decomposition. So assuming that I know the zeros of the dispersion relation of the complex of the porous plate region, I can move on. And the useful thing to realize, and I alluded to that a couple of times during the talk already, the useful thing to look at or to realize is again that basically the base problem, if you like, is the one where you just have an impermeable plate, what people call the dock. And if you look at the roots as perturbations of this dock problem, where the plate is impermeable, where the mu is 0, then it's reasonably all right to track those roots. Anyway, we can do that. It's a slightly tedious calculation, but it turns out that this f of s, this thing that I split up and evaluated as a Cauchy integral before, actually has this infinite product decomposition. Okay, and you see what I need for that. Unsurprisingly, is I need exactly the roots of the dispersion relation in the porous plate region, which is something I wanted to avoid, but just to show you that this can be done. Okay, if I can move on, I can now evaluate this I, my integral, and if in the end I arrive at this expression here. Remember, the reflection coefficient was e to the minus 2I kappa, I think, theta of kappa, and the theta is exactly this phase here, which now doesn't contain the I anymore, but contains these additional summons coming to do with the roots of the dispersion relation in the complex plate in the porous plate region. Okay, so how do I do the finite plate? So from a sort of Wiener-Hopf solution type of idea, that's all good. I've basically solved the problem completely. What about finite plate? Of course, I can't do that with the Wiener-Hopf method, but I can do it with something rather closely related. So what I do now is, I should probably have some, perfect. What I do now, I come closer to the problem. I come closer to the problem in my wave flume. I install here at A a rigid wall. And of course I can't solve that by the Wiener-Hopf technique, but I can solve it as follows. So now I come back to the idea with the vertical eigenfunctions, and I look at the eigenfunctions above and below the plate. And they're given as this thing here. This is again just from a separation ansatz, a very simple computation. And these factors in front here, I choose them to meet the first plate condition, which is this one, and I normalize them. Okay, and then what I have to do is I have to satisfy the second plate condition here as well, the thing that the velocity has to be equal to the jump in pressure. And if I do that, I get this auxiliary condition, which, unsurprisingly, is precisely again the dispersion relation in the porous plate region, which we've already seen many times as the denominator in the Wiener-Hopf kernel for the semi-infinite plate. Right. So if I do that, so now I basically do what I've alluded to before. I write my potential now on the left-hand side. This is my phi minus, in terms of the eigenfunctions on the left-hand side. I do the same thing on the right-hand side, but with the appropriate eigenfunctions there, where I have this nasty dispersion relation to worry about. And I match the potential and its and the horizontal velocity across this line x equals 0. I multiply by these eigenfunctions, integrate, and now I could truncate and solve numerically. That would be the standard method, but I want to show you that I can actually do more than that. And what I can do is I do the following. I just move on and I eliminate Bm. Bm, just to go back here, Bm is the expansion coefficient in the porous plate region. So then I'm left with this thing. I rescale my A just for notational convenience, and I note that the reflection coefficient is now just the A naught. Right, so what I could do, just to sort of show you what happens, I could neglect the terms involving these exponentials. The A is precisely the length of the plate, right? So if I drop these terms, that would mean letting A go to infinity, which is precisely the semi-infinite plate problem. If I do that, then the system simplifies, and I can ask the question, can I solve that? I'll get back to the finite plate problem in a second, and I can do that by the following observation. I look at if I look at these numbers here, Im, which are integrals over sequences of circles of this radius centered at the origin, so they become larger and larger and larger, and the function f is a function which has simple poles at minus kappa naught, and then all those kappa n's, those were the roots of the free surface wave dispersion relation. Then this goes to 0, and so I can say this thing is 0, but on the other hand I can compute these things by the residue theorem. And if I do that, then the equation I get is this thing here. So all I've used here is that f goes to the limiting behavior is ff, as well as the that I know where the roots are, which I place precisely at the roots of the dispersion relation. And now I compare, and this is the I compare with my system before. I just go back one slide, look at this system here, and look at this thing here, and I realize they are exactly the same if the A infinity is the residue of f at kappa n, if I want this to be 1, and the R infinity is precisely this residue. Right? This is just a simple inspection. If I go back here, I look at this equation, and I look at this equation, then if these things are equal, then they're exactly equivalent. So what I do is I look at my f, and I write it in as an infinite product decomposition because I know all the roots, and I can make sure that the infinite product converges. This is slightly tedious, but I think also in this community rather well known. And then if I go back, I find that this R infinity is precisely this expression here, where the phase theta is given by this sum. And I won't scroll back 10 slides, but I hope you believe me that this is precisely the same expression that I got by the Wiener-Hopf method using the standard infinite product decomposition. So I can actually, so I recover the Wiener-Hopf solution by this residue calculus method. For the semi-infinite case, of course. What about the finite plate? The finite plate, I go back and I do the same argument, and it turns out that here I can only get a rapidly convergent expression for R. So I go back, I look now at these integrals Jm, where I have to include the exponential factor here. Now I want to do the same thing, right? I want to compute the residues, and I want to compare to the system of equations that I have to solve. So I do that. Problem here is that that my lambda m's, my roots of the dispersion relation, are actually not automatically zeros of f in this case because of this this additional factor. But what I can do is, it turns out that those bm's, these ones here, if they have to satisfy this thing here, with the operator, or the sort of the discrete operator kmn here, given by this expression and this behavior here. If I have that, then I can move on. So can I solve this system? Yes, I can, under some assumptions which are basically given down here. So when are these satisfied? Well, they are satisfied if you inspect the thing closely, if the lambda naught times a is sufficiently large. So that means either the wavelength is sufficiently large or the plate is sufficiently large. So if the wavelength is very small and the plate is very short, then that doesn't work. So that's a sort of a slight thing to realize sort of alongside. But typically, at least for typical cases we tested, it always worked fine. If I can do that, then I find that my R is actually the R infinity, so the reflection coefficient of the semi-infinite plate corrected by this thing here, where the B's are precisely the solution of the system just from the previous slide. And I can even go further and just look at the first term approximation. I just look at the B naught. I can very quickly pull out what that is, and I'll show you in some numerical comparisons soon that is actually a very good approximation in many cases. Right, but anyway, what you get is this expression here. Right, so let's look at some numerics. So first thing we do is we compare the reflection coefficient for the semi-infinite plate, calculated using the expression from the Wiener-Hopf approach with the Cauchy Integral Method, to the results from simple eigenfunction matching. And I have some numbers here. It's not so exciting. What I just want to point out is that the convergence of the eigenfunction matching is rather slow. You need a lot of roots, and they're quite tedious to calculate. Maybe these are slightly more exciting, just to show what's going on. So what is this plot? This is the modulus of the reflection coefficient versus kh, k being the incident wave number, h the water depth, and you see different lines here for different submergences of the plate. And what is so you sort of see what you would expect. So for porosity parameter sigma 0.01 here, and you see sort of what you would expect. So if the plate is either rather close to the water surface, then of course the surface waves through the plate more, so you get stronger reflection. So as you go down with the plate, which means this number decreasing, you get weaker reflection. And on the other hand, always if the waves get shorter, also they don't feel as far down what's underneath. So as the waves get shorter, the wave number gets larger, and the reflection coefficient becomes smaller. And you can see this plot here. This is again R infinity and modulus versus kh, but now for different parameters of porosity. And also what you would expect is, it happens as expected. If you increase the porosity parameter, the reflection gets larger. Gets smaller, because you dissipate more energy. Whereas if the porosity parameter gets smaller, the thing behaves more and more non-permeable, so you get stronger reflection. Right. So just as fourth decimal place accuracy is obtained by the semi-infinite plate residue calculus by truncating at very small numbers, which is very neat and validates the applicability. And I'll also show you some finite plate numbers here, just again to show you the convergence and the residue calculus zeroth term approximation, which was this very, very simple expression, already gives quite good results. Right. So that's sort of the long story for the porous plate. So what happens with other plates? And I should sort of hurry up a bit, but so what happens? So let's look for example an elastic plate. So the porous plate condition was this thing here. It's still on the board. And basically, all these conditions, what they always say, whenever you put plates there, is you need some condition, obviously, for the potential and the velocity. So the porous plate was continuity of velocity equal to, or proportional, I should say, to the jump in pressure. If I look at an elastic plate, it doesn't look very different. Velocity has to be equal, and something has to be equal to the jump in pressure. Here I have not a 0th order operator, but I have a 4th order differential operator. This relates to the talk of Sasha yesterday, of course. And then I have boundary conditions for the plate. For instance, if I have the plate clamped, then the conditions are this with j equal 0 and k equal 1. Or if I have free edges, I have the same conditions, but for j equal 2 and k equal 3. And this is, so k is not the wave number here, of course, but it's in just this counting index. Right, but otherwise the whole thing looks quite the same. So what's going to happen if I can now sort of go back and try to sort of scribble out or sort of leave everything as before, and whenever this stuff appears, I have to change the whole derivation, right? And where is it going to change? It's precisely going to change at those places where I have to worry about the dispersion relations. So the Wiener-Hopf solution method will look exactly the same, except that the denominator in the function to factorize will have a more complicated dispersion relation with powers of k coming in due to the 4th order operator here. And if I want to do the residue calculus technique again, I have to worry precisely about that. And the other point where it comes in is because I have this higher order operator here. If I let the functions, my plus and minus functions, go to infinity, they won't go to 0, but they'll be a 2nd order polynomial. So I pick up 2 unknowns, and these I precisely need to match the boundary conditions. So I think I've briefly summarized that here, and I see my time is running up. So I should probably leave it at that and just again say, so numerator is the same, denominator exactly picks up the dispersion relation. Yeah, and I've already said that, so I should probably just leave it at that. There's a couple of pictures here just to show you that the modes can look very funny with the submerged elastic plate. And yeah, maybe I'll skip this and come to my summary. So if you have these problems, eigenfunction matching works easy to formulate, but it can be quite nasty numerically. But Wiener-Hopf technique and Cauchy Integral Method works very well for the semi-infinite problem, and the associated residue calculus method can be used very nicely to compute the problem for finite plates. And this applies to other thin horizontal structures. We can do it for elastic plates. It should also work for membranes. You get a 2nd order equation, and so basically you can sort of copy the whole method as is. And always what you have to know is the dispersion relation. So if you know about the physics, and this is sort of also a method I want to a message I want to stress on. If you know about the physics, if you know about the roots of the dispersion relation, that's very important for being able to come up with nice factorizations. Right, and the other thing I also want to point out, what would be interesting is, and I haven't looked at this to be honest, is to have multiple plates, right? Because that's actually what people particularly install at the end of these tanks, and then of course you get a much more complicated dispersion relation, or talking from the Wiener-Hopf viewpoint, you get matrix problems which you have to worry about. Okay, I think I should really leave it at that. Thank you.
I have 3 questions, but
right.
Simple. First of all, if the porous plate is placed from minus infinity to infinity,
yep.
Does it prevent any sinusoidal wave to exist?
No, that's a good question. I would imagine that you always get because of dissipation.
Okay, so in your case, if it is semi-infinite,
yeah,
the wave decide?
Yeah.
Okay, so it prevent?
I would expect that, yes.
Does prevent. Okay, and second, when it's semi-infinite, what part of wave energy is dissipated and what part is reflected?
Yeah, well, you can basically measure that in terms of the reflection coefficient, and you can sort of see that in my plots.
Would you, in principle, to draw how it depends on something?
Yeah, no, this is at least related to these plots here, right? Because here that's the modulus of the reflection coefficient.
Reflection.
Right. So basically, if the modulus would be 1, it would be fully reflected, but it's not 1, so energy is dissipated, and you can. I mean, this is basically a proxy for the amount of energy being dissipated. But of course, knowing that, you could.
And where is it dissipated?
Where is it dissipated? It's dissipated basically as friction within the porous plate.
Polar points or in porous?
In the porous plate.
In porous.
It's in the porous plate. Yes. Yeah. If the plate, I didn't get into this, but if what you can very simply do in this problem, once you've worked out the solution, you can set the mu equal to 0, no porosity, and you can look at the reflection coefficient, and there's always modulus 1.
Okay.
So dissipation is fully due to porosity.
But the strange effect that the porosity, if the porosity becomes higher and higher, you actually no longer dissipate energy, it becomes rigid.
Yeah.
If porosity is 0, then it just flows freely. There's an optimal porosity.
There's an optimal porosity. Yeah. No, that's very true. No, that's a good point. Yeah. I probably should have said something in that direction. You're totally right.
Okay. I've got a question about your basic formula, about slide 12.
Slide 12. Sure.
K plus and K minus.
Let me slide 12. This one.
Been a bit before.
Bit before.
Yeah.
Oh, you mean this one, probably?
No.
No?
Not that one. Here we are. If you take, for example, your formula for R infinity,
Yeah.
in the numerator you've got K plus times K minus there. So my question is, are there particular values of kappa such that that product of the K plus and K minus equals 1? Now, I have a reason for asking that.
Okay, yeah, go on.
In the comparable problems in diffraction theory, this does occur, and this particular value has great significance. And it's a different problem, and it relates to where a simpler theory happens to be exact. There's a Kirchhoff theory,
Okay.
in which the critical result is how radiation depends on direction.
Right.
And in that problem, where this product equals 1, the approximate theory is exact, and that's a really significant direction.
Okay.
Purely speculative, but if there is such a value, and you can see what would happen here, you see
Yeah.
your formula there
Yeah.
has a much simpler structure,
Yes.
and therefore there might be an elementary theory analogous to the Kirchhoff approximation in
Right.
electromagnetism,
Okay.
gives an exact result. And this approximate theory would involve some really naive assumption about boundary values or boundary derivatives. That's purely speculative.
Okay. Well,
It's not an analogy.
there are quite I mean, there are lots of plus minus functions appearing here, and I remember there are some for which that is actually true. I don't think it's generally true for the K, but we can.
Anticipation, it might rule it out.
Yeah.
You
Yeah.
never know, it just might lead to something.
No, it's interesting. Yeah, we should talk more about that.
I just want to make one more comment. Of course, as you mentioned in acoustic, that kind of problems with plates have occurred quite a lot.
Yes.
I think there's a lot of people who have worked on this.
Yeah, I mean, this is just a special duct, right, if you like.
So we can discuss further.
Yes. Yeah. No, definitely.
Okay. Shall we move on? Thank you very much.
Thank you.